followed by a PhD in aeroacoustics and acoustic engineering at ETH in Zurich, in Switzerland, in 2020. After a postdoctoral and lecturer position on ultrasonic cavitation, still at ETH in Zurich, she joined Silicon Austria Labs in Villach in Austria as a senior scientist working on acoustic MEMS development and characterization in 2022. In 2024, as I mentioned, she became an assistant professor within the TUE in the Dynamics and Control group. She's working right now in aeroacoustics for complex engineering, and she will be talking to us about her presentation titled How to Incorporate Fluid Structure Interaction into Low-Order Modeling of Thermoacoustic Instabilities. So thank you very much, Claire, for being with us today, and please, the floor is yours.
Thank you so much, Claudia, for the kind introduction. Also, thanks for reading that extremely long title. So that's actually what I want to start with. So yeah, this is a long title, and there's 3 main parts to this title. So I just want to make sure that we all know what we're talking about, right? So I'm going to start by the end, actually. So I'm going to start by introducing to you what are thermoacoustic instabilities. Then how do we perform some low-order modeling of those instabilities? So a bit of a disclaimer, although this is a talk from the Combustion Institute, I am by no means a combustion expert. I'm more on the dynamics modeling side. So yeah, for those of you excited about the combustion chemistry, unfortunately, I have to apologize in advance that we're just going to model the flame with some Taylor expansion. That's more or less going to be it for the combustion part. And then as a third part, it's going to be about the fluid structure interaction. So I'm actually going to go a bit back and forth, but I put those 3 little icons that you're going to see on the top right. So you know kind of what is the main topic of the slide. Either we're talking about thermoacoustic instabilities, the low-order modeling, or the fluid structure interaction. And hopefully then you don't get lost in this presentation with the lengthy title and a lot of different physics involved. Okay, so first things first, thermoacoustic instabilities. So I'm assuming maybe not all of you are familiar with it. So where do we find them? So typically they can be found in aero engines, in gas turbines for electricity production, in rocket engines, so liquid propellant engine, and in industrial furnaces as well, which was the original topic of the NWO funding that is at the source of what I'm going to show to you today. So what are they? So just as a simplified explanation of what happens in a combustor where you do have thermoacoustic instability, so you've got a coupling between an acoustic mode of your system, so typically between the fuel and air injection, where you would have choked conditions, which acts as a hard acoustic boundary condition. And then within the whole volume of your combustion chamber, you can have acoustic modes that are the eigenmodes of your combustion chamber. And then in some cases, it happens that the flame, and specifically the heat release rate of the flame, is synchronized to the acoustics. And this is measured. Sorry, I'm just going to reduce you guys because you're in the middle of the slides. Yes. That is measured by the Rayleigh criterion. So it's a criterion where you integrate over one period of your typical acoustic quantity the unsteady pressure and the unsteady heat release rate. And of course, if the integration over one period of this quantity is positive, this means you have energy added to the system, and this is when you can reach instability. So the amplitude would keep growing and growing until some nonlinear mechanism makes it reach a limit cycle. But we're going to go a bit more into that. Yes, okay. So this is a very, let's say, simplistic view. You just have the acoustic eigenmode and the flame. I just want to, so we're not going to go deeper in the modeling for today, but I just want to make you aware that there are models that take a lot more physics into account. So I think usually it's quite scary to show this graph from Wolfgang Polifka in Munich, which shows you basically everything that can come into play when you're looking at thermoacoustic instability. So we're doing a very much simplified version today. But as you can see, you could also take into account entropy waves, some coherent flow structures, some coherent flame structures as well. So there's a lot more to it, but I'm just focusing on a very simple modeling. But just so that you are aware that this is a much more complicated problem. Okay, and then so what are the consequences? So when you do have thermoacoustic instability, so your amplitude typically can rise very high. So this and it depends on the conditions of your combustor. So typically the equivalence ratio and the fuel mass. So this is an example from a colleague of mine from the PhD. Where you can see that on this equivalence ratio versus natural gas mass flow map, you have some places where the RMS pressure that is measured by some microphones is quite low. So in that case, you have no clear dominant peak in your frequency response. Of course, you still have some frequencies that dominate if you really zoom in on the responses, but then the amplitude of your pressure fluctuations is really staying close to zero, and the distribution is really has this shape with a very sharp slope close to zero, and then an inflection point after the peak. And then in some other cases, so typically in that case, when we go more lean and we add more air to the system, we can reach a case where the pressure fluctuations get very high. And then the typical diagnostics tool that you can use to determine if you have an instability or not is, okay, so very clear resonance peak in the frequency response, knowing, however, that this is not sufficient, right? You could have a system that is resonant and excited by something else at some of its resonance frequency, for which you would then have a very high peak in the frequency response, which does not necessarily mean that you have an instability. But in that case, so of course the amplitude is way higher, as you can see, but also if you do the statistics on the envelope of your pressure fluctuations, you can see that the statistics of this amplitude, of this instantaneous amplitude of our pressure fluctuation, is not anywhere close to zero, and it shows rather this shape, so like a Gaussian distribution around a certain mean amplitude that you would have. And this we're going to use later for some of the low order modeling. Okay, so in terms of consequences, you might be like, okay, the acoustic pressure is high. Do we actually care? So the answer is yes, of course. So maybe some of you have seen some of those horror pictures so this is from liquid rocket engines, liquid fuel rocket engines. So some pictures from NASA of some catastrophic explosion or flame flashback that led to melting of some injectors or total deformation of the injectors as well. Then for gas turbines, we also have the equivalent of some. So typically the main danger is that your flame, instead of sitting in the combustion chamber where you had planned it, is either blown off or moved upstream by the pressure waves. And in that case, of course, you heat up pieces that were never designed for those high temperatures. And this is what happens here with everything that is damaged by high temperatures, basically. So yeah, those are some of the dangers: flame blowout and flashback, leading to structural damage as well, as you can see on most of those pictures. But actually, so we always tend to mention a bit too much those spectacular cases. But even if you're at moderate amplitudes, you still want to get rid of them, because besides those spectacular cases, the consequences of thermoacoustic instabilities are also reduced engine efficiency and increased emissions. So you also do want to get rid of them, not only in the extreme cases, right? And also there's a slight shift of paradigm with, I think it's the same among the whole combustion research. I guess this is probably the one point where we where we are on the same boat, is that progressively we're switching all the combustion fuel from methane and natural gas to hydrogen, or at least we try to increase the hydrogen content for ecological reasons, obviously. And so this does not necessarily mean that it's more unstable or more stable. It really depends on the cases. But in any case, the hydrogen has very different combustion dynamics. So there is a lot of leverage at the moment to also, improve the modeling that we have of thermoacoustic instabilities, especially in the case of H2, because the dynamics are quite different. Okay, so now a bit more on the low order modeling of those instabilities. So I go back to my simplistic view of, okay, we have typically a first acoustic mode and the heat release of the flame that would sit somewhere here, that couple to give out this thermoacoustic instability. So the simplest way to model this is actually to separate the, to do some Galerkin expansion on the pressure in the combustion chamber to model it as the sum of terms which relate to the different acoustic modes. So typically in that case, the psi I would be the mode shapes of the various modes, and then the eta I is the time amplitude, time-dependent amplitude of this mode. And then so typically in this frequency response, you have the response of multiple modes at the same time. So this is what you see here with two modes which would have various, very different mode shapes, but this is also not necessarily always the case, as I will show you later. And then, so this is the part where I start throwing scary equations at you, but I will walk you through it, so don't panic. So the main point of this modeling is that so for each of the time-dependent amplitude, we model it as a base with a harmonic oscillator equation. So that this is what you recognize here, that the second time derivative of the time amplitude plus the square of some frequency and the time amplitude again is equal to some forcing terms. So this is the oscillation part, right? So this frequency determines the period at which we oscillate. Then we have the linear decay or the linear growth of our system, which is defined by this term, which I will also expand later because nu is actually made up of multiple terms. But in a nutshell, so this nu is what tells you if your system is stable, meaning if you disturb it, it would go back to zero, or unstable, meaning the slightest pinch would give you the trigger to start developing a full-blown acoustic instability. Then the other source term here would be the flame nonlinear response and the modes coupling. So this is what gives you the actual dynamics, steady state dynamics of your system. And then last but not least, we have as an effect of the flow turbulence, we add a random amplitude, so which is by this noise source term. So in the present case, we're going to use white noise. There are some studies where they also use colored noise to take into account the fact that the turbulence spectrum has more frequency content in the low frequency compared to high frequency, but this is not something we're going to cover today. Okay, and then so the last ingredient for today, so as you see, we're first slide where we're talking about the fluid structure interaction. So what if the boundary conditions were not rigid? Because in all the previous modeling that I have showed you, we just assume our usual wall boundary conditions, meaning that the wall are rigid, and then that besides heat losses, which are included in the linear term of our forcing, we assume that the walls would have no influence whatsoever on the dynamics. So in that case, we just have the flame reacting to the acoustic mode, as you saw before. And then, so what we want to ask ourselves today is, what if some part of the wall is actually compliant and can be excited by the flow and vibrate? And what would be then the influence of a flexible wall boundary condition on the thermoacoustics dynamics? So that is the main question for today. And also, how do we incorporate that in the low order modeling that I have just shown you? Okay, so we're going to use some practical data for this. So I'm going to introduce you to the DynAF combustor that sits in Enschede at the University of Twente. I think we even have Berkal, Berksu Erkal, sorry, who's joining today. So if you have questions on the setup, I think he can answer all of them, hopefully. Okay, so this is what happens in this combustor. So we have a cyclone, which is not to be seen at the bottom here. Oh, wait, I'm gonna use my laser pointer. Exactly. So under here, there is a cyclone here through which the air comes and is swirled, and then the fluid injection is done right at the end here. And then so all of that is injected here at the bottom of the combustion chamber, which also comes here. And then this is where the flame sits, as you can see from those this imaging here. And then so the combustion chamber is around 300 millimeters length, or 250, and we have pressure sensors located on the side. So what happens with this combustor is that it is stable when no hydrogen is added to the mixture, so when it's just running on pure methane. But the acoustic pressure is increasing tremendously when we add hydrogen to the mixture. So we're going to look mostly at this case, so the case where the molar fraction of hydrogen is 0.8, because this is the point where we have the biggest instability. So that's what we're most interested in. Okay, so in that case, the window that that we had before through which we could look at the flame, we actually replace it by a steel plate of 5 millimeter thickness. So the reason why we're doing that, so we assume that this plate is perfectly rigid, which is what we want, right? In that case, this is a baseline case, so we do not want yet to look at what happens if the walls are compliant. However, we do want the temperature boundary conditions to stay the same, right? Because obviously, if we have different heat losses because we have a quartz window instead of a steel plate, we might have very different flame dynamics. And then what we're measuring is not actually the influence of just adding a compliant wall, but also of modifying the heat or the thermal boundary conditions of the flame, which is not what we want to look at. So that is why we replace one of the window by this steel plate of 5 millimeter thickness. And then we measure what happens. So as you can see, we get a very sharp peak in the pressure. And when we look then at the statistics, so here in the middle, you can see just the time trace of the pressure. And then so we look at the statistics of the amplitude, so the histogram of the amplitude of the pressure and of the envelope of our pressure. So this is what you see here. And as I mentioned before, the envelope is what we will use to perform our low order modeling. So this is what we're doing now. So back to a slightly modified version of what I showed you before. So we still have our oscillator equation part here on the left, and then our source terms, and then our noise excitation, white noise excitation here. In this case, so we model the source terms as follows. So we add the damping of our system here in the source terms. So alpha is the damping. So in this damping, you already have included basically heat losses that you would have, any dissipation you would have in the acoustic boundary layers on the walls of your chamber, losses that you might have from the flow structures, etc. So it's really an aggregate term for all different kinds of damping mechanism that you might have in your system. And then so in this term, we also have the flame response, and I'm going to spend one slide on that as well. So the flame response, obviously, we need to approximate it depending on the amplitude. And so usually the way people do it is to use this third order Taylor expansion, because so usually the flame response is asymmetrical, meaning we don't have a term of order 2 here. And so we have the linear flame response here, which then this beta added, so beta minus alpha would be then our linear growth rate, which I showed you before. And then this term is the nonlinear saturation mechanism. So this is what allows your instability to develop, to grow exponentially up until a certain point where it starts saturating, and this is how you stabilize your amplitude on an unstable limit cycle of a certain amplitude, which might be very high, so you want to avoid it, right? Okay, so this is about the flame modeling, and then so plugging. So we plug those terms and this one inside here, and then we arrive to this equation where we have, so again, our oscillator part, our linear growth rate, which is, as I mentioned, so beta being the linear response of the flame, alpha being the linear damping of the system, and then the nonlinear response of the flame here, and as before, our white noise excitation. So you might say, okay, this is some nice modeling, but you have a lot of parameters that you need to identify. How do you do that? So the way to do it is actually to assume that your instantaneous amplitude of the acoustic mode that you're looking at is of this form, so that you have a slow varying envelope of your signal, and then the oscillating part with also a slow, relatively to the oscillation, a slow varying phase. And then so by looking at the dynamics only of those slow varying parameters, so the amplitude of the envelope and the phase, you can get to the Langevin equations which govern those slow fluctuations. So now I've only written the one for the amplitude because this is the one we use to identify the system parameters. The phase we're not really looking at this moment. And so in that case, what we can do is to identify based on the shape of our amplitude, we have ways to identify the growth rate, the cubic saturation coefficient, and the level of noise that we have in our system. So I refer you to this reference if you want more details on how this is done, or to our paper, which I will also advertise later. Yes, and so in that case, to identify, so the dynamics of A are of the envelope are what we use to determine nu, kappa, and gamma, which is the noise intensity. Okay, in our case, though, so now I've only showed you when we have a very sharp peak. So in our case, when we zoom in on the peak that I showed you before, the peak actually shows that there's, a main instability at 203 hertz, more or less, but that there is also influence of at least one neighboring frequency around here, because our peak definitely does not have a nice shape where we can just fit one oscillator equation and be happy with it. So we have to be a bit more creative here. So what we came up with was to use a coupled system of two oscillator equations, two of them being unstable modes. In that case, obviously, so the beta and kappa, which are the flame response, those are the same in all the equations. That makes sense, right? It's the same flame for both of them. But then for each mode, what varies is, so alpha, the damping of each term, omega I, which is the oscillation frequency. And then in that case, we also added an ingredient, which is a time delay between the modes, which allows us to reproduce the dynamics better. So for the system identification, obviously, so we have to be a bit creative there. It's a two-step process. So first we estimate the parameters of the first oscillator as we did before. So assuming that this bump here does not exist and that it would be a perfectly sharp peak here. Then we estimate tau1, so the delay related to the first mode, which is estimated from the phase peak between the heat release and the pressure, which we can measure. And then we do some empirical fine-tuning of the parameters for the second mode to be able to reproduce the dynamics. And I will show you later that this works quite well. Okay, so now we go again to the introduction of the experimental setup for when we do add the flexible plates. So in that case, so this is where we replaced before with a plate that was 5 millimeter thick, but obviously we can add some other plates. And then so we have our 3 pressure sensors that I introduced to you before. There's actually another pressure sensor, which is before the entrance to the cyclone. So we are able to measure the vibration in the center of the plate through a laser Doppler vibrometer system. So you can see the little green dot here in the middle, hopefully. And then we also measure the heat release rate through photomultiplier measurements on the other side. So we do have a quartz window on the other side. So we only change the thermal boundary conditions on this side by adding the steel plates. Okay, and then introducing to you the plates that we will use and introduce to the system to see what happens when everything when the boundary conditions are compliant. So both of them have a thickness of 1 millimeter, and to characterize them, obviously we did want to characterize them not separately from the combustor, because the fact that they are at high temperature and might also be not a uniform temperature across the plate might be relevant to the response of the plates, right? So what we decided to do is basically to measure, to do the transfer function between the vibration that we get from the center of the plate and the pressure sensor that is at the same location, let's say at the same longitudinal location on our combustor, because so at the low frequencies that we're looking at, we assume that we only have plane wave propagation in our system, and thus this is a reasonable hypothesis that we assume that the pressure sensor, even if it's not exactly at the plate, that it can measure accurately which pressure we have there. And so this is what we get for, so the left plate is just a simple plate of 1 millimeter thickness. So you can see that the highest response that we get is around, so the first resonance frequency of this plate is around 540 hertz, more or less. And then we tried also a different plate with an added mass, because we wanted to try with a plate that had the same level of compliance, but a resonance frequency that was closer to the one of our instability, which is the one here. So it has a resonance frequency around maybe 190 hertz or something like this. Okay, so also on the validity of those measurements, you might also say, okay, but you did those measurements while you had the instability. So it is also true that the response here of the plate would be subject to maybe not being the linear response, because we know that the base excitation, so of course, ideally, we would want to have excited those plates with white noise, right, with a pressure fluctuation that has the same frequency content all over the frequency range, or the same amplitude over the frequency range. However, we excited it with basically the pressure distribution that I showed you before, right? The one of the instability. However, when we look at the results, so first we have a very high coherence, which, okay, we would also get if we have too high excitation in this range. But we can also see that it looks like the plate response follows basically what you would expect from a damped harmonic oscillator here. So this is how we basically infer that the way we do the plate in situ characterization is, makes sense, because the result looks sound, even though we do know that we excite the plate more around this frequency range than around other ones. So this also basically is a proof that probably the nonlinear mechanism that would go into the plate vibrations only would be triggered at very, very high pressure amplitude, and we're nowhere near those amplitudes. That is also reassuring, let's say, for the validity of our modeling later. Okay, so now we look at the effect of the flexible plates on the DynAF combustor frequency spectrum. So as you saw before, the dashed line is what I showed you before. So the dynamics of our combustor without the presence of plates. Then when we add the plate that has its resonance frequency close to the one of the combustor, we see that basically the frequency is a bit shifted towards higher frequencies. But other than that, the dynamics do not seem to change drastically. However, when we do add the plate that has a much higher resonance frequency, we notice that the pressure amplitude decreases significantly, and there is some competition between the first mode, so the one that was dominant before, and then the second one that is shown here, which is at so very close but slightly higher resonance frequency. Okay, so we actually wanted to check what are the mode shapes in both cases, because we thought maybe what the plate influences is actually the mode shape, and then it's not actually some dissipation mechanism that helps, let's say, damp one mode or favor one other mode, but just a modification of the acoustic mode shape. So this is what we checked here. So we, for each of those plots, I'm going to explain to you a bit what it is. So we take K2, which is the pressure sensor that it has the same longitudinal location as where we measure as the center of the plate, which is also where we measure our vibration velocity. So this is our reference sensor. And then for each frequency, we look at the phase between this sensor and the three other sensors. So K1, the one that is before the cyclone, and then K3 and K4. And we look at that, of course, quite close to the frequency of both our modes, which are the two vertical lines here. And so, as you can see, the black one is the one without plates. The blue one is the one of the plate with low resonance frequency, and the red one is the one of the plate with a high resonance frequency. So as you can see, upstream, there's not much change. I guess we also probably did not expect much change here. We do have a slightly lower phase between K3 and K2 and between K4 and K2, so in the combustion chamber. So there is a slight modification of the acoustic mode shape by introducing the plate. However, what you can also see is that it's almost exactly the same between the plate with high resonance frequency and the plate with low resonance frequency. So this does not seem to be impacted by the resonance frequency of the plate. So we can basically rule out that it's an acoustic mode shape modification that modifies the dynamics of our system, because both those plates lead to a very similar acoustic mode shape, but to very different dynamics. So we know this is not the case. Then one other check that we have done is how much power is actually transferred to the plate. So in that case, we calculate the power by taking the real part of the convolution between the pressure and the conjugate of the velocity in the center of our plate. So that is the power transferred at one point. Of course, we need to integrate this over the area of the plate to have the global power that is transferred to the plate. And so what the approximation that we make, since we're mostly looking at frequencies which are around or before the first eigenmode of the plate, that we can use our plate transfer function to calculate this and multiply it by a term that depends on the mode shape. So in our case, we use this one, so the one of the first mode, because let's say, so even for the plate with the low resonance frequency, we might be a bit after, let's say, the first mode, but we're still very far around the 200, 210 hertz. We're still very far from frequencies where we would need to look at the second mode, basically. So this is an appropriate assumption. Okay, and then so what happens is when we make this calculation, if the transfer global power is negative, this would mean that the plate would transfer power to the system. So in a way, this is a description of a constructive interaction that you would have between the plate and the dynamics of your combustion chamber. And in the other case, if the total power is positive, this means that the plate absorbs power from your system and stabilizes it. So this is those are the results for both plates. So in black, you can see the frequency response that you're used to, that you saw before. In blue, this is the frequency response of the plate with the low resonance frequency. So as you remember, this was almost the same as the one without plate. And then in red, you have the frequency response of the whole system with the plate with the high resonance frequency, where you can see that there is a decrease in the main mode and an increase in the neighboring mode here. In pink, you can see the amount of power that we calculated is transferred to the plate. So you can also see that, of course, when we do have an acoustic, high acoustic amplitude here, this is when we transfer the most energy to the plate, which makes total sense, right? And then, so at the background is colored as function, so not only of the, let's say, the amplitude of the power, but also whether it is positive or negative. So what you can see is that before the occurrence of the first plate mode, you are systematically dissipating energy, so absorbing energy. Let's say the plate is absorbing energy from the system. But after the first mode, this is not guaranteed anymore. And so in the case of the flexible plate with highest resonance frequency, we can see that since the first mode of the plate is somewhere here, we are absorbing energy from the system over this whole frequency range. So now we want to see how do we model the plate to add it to our low order modeling that we saw before, right? So the first option would actually be to use also an additional harmonic oscillator for the plate. So this is something we would be able to do. So to fit basically the plate response by a simple oscillator equation like this. So fitting the omega, so the frequency of the first mode, and gamma, which would be the mode damping, to this plate frequency response that we calculated before, feeding it with the pressure, and then adding also to our system of coupled equations that we had before, some source term which would come from the volume, the volume variation, which results, so the volume variation in the combustion chamber that results from the displacement of the plate. So we actually ruled out to use this modeling because in that case, we would have expected the plate with low resonance frequency to have way more influence on the system dynamics, which was not the case because, so if we would add this harmonic oscillator, which would have an eigenvalue really close to the current eigenvalues of our system, we would have a tremendous effect on it, but not if we would have an eigenvalue that is far from it, which is not what we saw. So the second option is to increase the damping of some of the modes. And so this is what we did here. So I'm going to show you here. So the black and purple arrows here are the eigenvalues that were linked to our system before we added the plate effect. And then to model the plate effect, so what we add here is that we decrease the growth rate in practice of our main mode by an amount of damping that we fit to the dynamics here, and which represents the added damping of the plate vibration. So as I mentioned before, since in the damping of our system to begin with, we also had included whatever dissipation happens at the walls, right, in the acoustic boundary conditions. So this is not such a far-fetched hypothesis to assume that the vibration of the plate just increases the dissipation at the wall and results in higher damping overall. And yes, so then with the new eigenvalues, which would be then the green one here and the purple one here, so we are able to reproduce nicely a frequency response here. What I want to show you is also to compare so with and without plate. So maybe I need to go back to explain to you what's happening on those plots. So in the model, we have two oscillator equations here. And for each of those modes, we can calculate the amplitude and then check the amplitude of both modes separately. In the experiments, however, we have only one pressure time trace, right? So we would not know when we are at which mode. So the way that we generated also this amplitude distribution between the two modes is to filter basically the signal very narrowly around the two peaks, so in a range here and then in a range here. And this gives us some kind of probability distribution, whether we're more in the dynamics of the first mode or in the dynamics of the second mode. And this is what I'm showing you here. So without plate, as we can see here, so we have the amplitude of the first mode, so the one that was at 203 hertz, that is very high, and then the amplitude distribution over the second mode is quite low. So sometimes we have some incursion that the pressure actually goes to the second mode, but most of the time the oscillations happen at 203 hertz. So we are able to reproduce this nicely with our system. So that's the system identification that I showed you some slides ago, where we first estimated the terms for the first mode and then adjusted the terms of the second mode so that it would match this probability distribution. Then once, also when we do model this, we can then look at the separate two amplitudes, and this is what we also see here, right? That for the first mode, most of the time, this is our pressure and time trace, and then only, so the modes are mutually exclusive, right? So either we're at one of the frequencies or at the other, and this is what we see also in the experiments. So if we look at the statistics of the time instance where the pressure is here, those corresponds to specific quite lengthy intervals, and then some other intervals you are around here, but we can really separate basically when we are in the first mode and when we are in the second mode. And then once we add our additional damping from the plate, so this is what we get from the model, so where we get quite nice intermittency between the two modes, and where it's way less obvious which one is dominant. So we really have a modal competition between the two modes thanks to additional damping of the plate. We can see that this is also quite in line with what happens experimentally. So again, this was generated by filtering around the two modes and then making the statistics of those filtered amplitudes. Okay, so coming up to my conclusions. So we combined laser Doppler vibrometry and pressure measurements to investigate the influence of a flexible boundary on burner dynamics. So a bit counterintuitively to what we expected, this is not the plate with the highest resonance frequency that, with the resonance frequency closest to the thermoacoustic mode that had the greatest influence on it. We're actually quite surprised how little influence the other flexible plate had. And then so we can also conclude from our power analysis that positive power transfer from the fluid to the plate seems to be only guaranteed before the first mode. And on the modeling side, this is still on the physical side. So the plate with higher resonance frequency leads to modal competition between the modes that are close. And it seems to be that the best lower the modeling strategy is to increase the damping of the most unstable mode, at least in our case. However, if there are some cases where the plate would have a high influence and would be with a resonance frequency close to the frequency of instability, we suspect that modeling the plate as an additional harmonic oscillator could be appropriate. And last but not least, on a lighter note, actually the added mass on the second flexible plate sadly left us after 2 days of good services during the experimental campaign. So yeah, in loving memory of the plate with added mass. And then so if you want more details, there is also this paper titled Low Order Modeling of the Thermoacoustic Instability with Fluid Structure Interaction Effects. Yes, we love long titles, which is going to be submitted soon to Combustion and Flame. And yeah, last but definitely not least, I would like to acknowledge basically the two most valuable players of this study, which is Dario Passato, who took care of the modeling, and Berksu, who generated the experimental data. And I would like to thank Jim Koch, Ines Lopez Arteaga, who are also in the DNAV project. I would like to thank NWO for financing this project, University of Twente for being able to use their labs, and Giacomo Bonciolini for providing some of the nice figures on the low order modeling for this presentation. This is it. I'm open to questions now.
Thank you very much for the really interesting presentation, Claire. It was really nice. And I'm not in the field of thermoacoustics instabilities, so it was really nice that it was very approachable for the people that